Hello, I'm Ying from Institute of Software Chinese Academy of Sciences. I'm going to introduce our work, finding bugs in Gremlin-based graph database systems via randomized differential testing. Graph data consists of vertices and edges, in which a vertex represents an entity and an edge describes the relationship between two entities. Graph database systems support efficient storage and queries for graph data. We will call them JDBs for short. Examples are Neo4j, OrientDB, and so on. The popularity of JDBs has increased dramatically. For example, Neo4j has been downloaded 2 million times. Nowadays, JDBs play a significant role in numerous applications, such as knowledge graphs, social networks, fraud detection, and medical. Most GDBs are built on the labeled property graph model. In this graph model, each vertex and edge has a set of properties and can be divided into different groups by its label. Graph query languages are diverse, and there is no standardized way in JDBs to query a graph. Fortunately, around 66% JDBs support Gremlin APIs. Gremlin is a functional query language and links a sequence of Gremlin API calls for traversing labeled property graphs. For example, we want to know how many people are between 20 and 35 years old. We first get all vertices. Then we filter vertices with the condition that the person's age is between 20 and 35. Finally, we count the number of persons that match the filter condition. Unfortunately, those GDBs can be buggy and result in incorrect query results, such as omitting a vertex or throwing an unexpected error. These logic bugs can lead to severe consequences, such as error diagnosis in medical applications or error detection in fraud detection application. Here is a real logic bug. In this example, we want to know how many people are between 20 to 35 years old or under 29 years old. We execute this Gremlin query in huge graph. The expected result is 2, but huge graph returns an incorrect result 3 because huge graph forgets to deduplicate overlapping values for all operations. There are many tools and approaches for detecting bugs in relational database management systems, also called RDBMS. For example, RAGS and Apollo utilize differential testing to detect bugs in RDBMS. SQLsmith and AFL generate random SQL queries for testing RDBMS. Two metamorphic testing approaches are proposed to solve the testing oracle problem. However, all of these tools or approaches cannot be directly applied to GDBs. Thus, the goal of our research is finding bugs in GDBs that adopt Gremlin to retrieve graph data, also called Gremlin-based GDBs. To achieve this goal, we propose GRound for automatically finding logic bugs in Gremlin-based GDBs via randomized differential testing. The core idea of GRound is to construct semantically equivalent databases for multiple JDBs and then compare the results of a Gremlin query on these databases. So here you see, GRound includes 3 steps. First, GRound generates random graph database and writes it into target JDBs. Then, GRound constructs a transverse model for Gremlin APIs, and then generates Gremlin queries based on the constructed transverse model and the generated graph database. Finally, GRound executes the generated queries in target JDBs and validates the query results by differential testing. I will explain these steps one by one. The first step is to generate graph database. GRound first generates graph schema including vertex types and edge types. Especially for each vertex type, we first randomly generate its label name, and then we generate a set of property types, including property name and data type. To generate an edge type, we first randomly choose two vertex types as its incoming and outgoing vertices. Then we use the same way to generate its label name and property types. According to the generated graph schema, Geronda further then generates the graph data. For the vertex generation, we first randomly select a vertex type. Then we randomly generate property values of this vertex type. Note that we randomly select a subset of property types, so we can generate a vertex whose label is book and only has a title property. For the edge generation, we randomly choose an edge type. The properties for edge generation is the same as that in vertex generation. We then randomly select one vertex that can form edges incoming or outgoing vertex type. The second step is to generate Gremlin queries. Gremlin has different syntax and query patterns from SQL. Therefore, the existing query generation tools in RDBMS cannot be used in GDB testing. To generate Gremlin queries, we should study how to legally link Gremlin APIs. Gremlin provides many Gremlin APIs for constructing a traversal in a graph. So we can choose Gremlin step completely random from these provided APIs. However, some grammatically correct but meaningless queries may be generated, and the semantics of Gremlin APIs may be ignored, which can greatly affect the effectiveness of GDB testing. Therefore, we construct a model to guide us in generating syntactically correct and valid Gremlin queries. We first analyze the constraints about how to link Gremlin APIs and found that the input type of a Gremlin API in a query should match the output type of its previous Gremlin API. For example, the person's alt edge is read, so for the API alt E, its input should be a vertex set and its output is an edge set. And such, we can link the API alt E after API V, but not link it after API E. Based on this observation, we abstract three entities, including vertex, edge, and value, and construct a transverse model to describe the legal operations and semantics in these entities. Especially, we can traverse the vertex V1 from the vertex V2 by using API out, or from the edge E1 using API in V. We can also filter it by the given conditions. For example, we can retrieve the vertex V1 using API has with its property key VP1 as a parameter. The traversal model also describes the legal operations on edge. We can traverse the edge E1 from the vertex V1 using the API in E. We can also retrieve it through API has with its property key EP1 and a predict as parameters. Here, the predict checks whether the incoming number is greater than 3. For the legal operations on values, we can retrieve property values belonging to vertex or edge using the API values. We can also aggregate property values with API sum to compute the sum of properties. Based on the above transverse model, we can generate syntactically correct and meaningful Gremlin queries. Geronda randomly selects Gremlin API until the maximum query length is reached or exit condition is satisfied. Take an example. At first, the query is initialed to a Gremlin graph traversal source G. Then, Geronda randomly selects a vertex API V whose output type is vertex. Next, Gerund randomly selects a filter API has with a proper name and a predict as parameters. Due to the input of API has is a vertex set, the property name should be a vertex property name. Further, Gerund randomly selects a predict type and the second parameter. Next, Gerund generates a value API values with a vertex property name as a parameter. Since the API returns some values, the exit condition is satisfied, and Gerund will stop generating the next Gremlin step. You may find that there are many parameters in Gremlin query statements. Completely random parameter generation may return lots of empty results, which can greatly affect the effectiveness of GDB testing. To achieve it, two strategies are proposed for parameter generation to increase the probability of returning a non-empty result. On the one hand, we randomly select property name or value from the generated graph database. On the other hand, we generate a random value. We randomly use these two strategies. In the third step, we use the differential testing approach to solve the problem of testing oracle. We execute the generated Gremlin queries on target GDBs. By comparing the return results, we identify a description and a potential bug. However, we found that the result formats of multiple GDBs are different, which makes it difficult to check the return results. As such, we convert the query results from different GDBs into a unified format. To achieve this, we first generate a unique ID (UID) for each vertex and edge. Then, we retrieve its actual ID stored in GDB as actual ID. We use a mapping table to record the mapping relations between UID and actual ID in all GDBs for each vertex and edge. According to the mapping table, we can convert these query results into unified formats and easily verify the unified query results of all target GDBs. To demonstrate the effectiveness of Gerund, we evaluate Gerund on 6 widely used GDBs and detect real-world logic bugs in them. We configure Gerund to run 15 times and generate 1,000 random Gremlin queries in each time. For each reported description by Gerund, we manually reproduce and analyze it to verify whether it's a real logic bug. Finally, we found 21 logic bugs among 709 descriptions. In total, Gerund detected 21 bugs, in which the developers have configured 18 bugs and fixed 7 bugs. We also evaluate the instruction coverage of Gerund. Experiments show that Gerund can achieve coverage from 32% to 61% for query engines and 16% to 42% for target GDBs. I finally conclude our work. To find logic bugs in GDBs, we propose a model-based query generation approach to generate valid Gremlin queries and a data mapping approach to unify the format of query results for different GDBs. Experiments show the effectiveness of Gerund. That's all. Thanks.